This lecture is entitled What's So Special About Relativity? We have a quote from Albert Einstein. It says, "It is every man's woman's obligation to put into the world at least the equivalent of what she takes out of it." So, the goal of this presentation is that you be able to distinguish between special relativity and general relativity. Special relativity deals with the speed of light and implications that deal with the speed of light. General relativity deals with gravity. It is important that you understand the thought process behind relativity and the evidence that supports it, and identify applications of these theories in everyday life. I am not going to ask you to solve relativistic equations that involve calculus and three-dimensional structures and space-time. It gets to be extremely confusing, but it is important that you understand the ideas that are behind them. Now, what we already know. We know there's no absolute reference frame. We know that if you're walking and then a car goes the other way, that it appears to be going faster than it actually goes. We know that the movement between objects is relative to one another. So, in other words, if I'm walking this way at 5 meters per second and somebody's walking this way at 7 meters per second, it appears to me like this person is moving at 2 meters per second. We've talked about that already when we talked about motion. We also know that nothing can move faster than light. Okay, that's one of the things we talked about, that the speed of light is an absolute value that you cannot exceed. We also know that Newton's law of universal gravitation was sufficient to explain the motion of the planets. So that's stuff we already knew. Now, what we learned in the lab was this, that gravity can be used to bend light. And that's kind of weird. A lot of people didn't really like that. But if you have this idea that this right here is some sort of gravitational object, it can bend the light. And when it bends the light, it can be used by telescopes to view objects very far away. So if I can't bend that light sufficiently, I can use something like, I don't know, a black hole or some sort of supermassive body in order to bend that light. Mass can be used to bend both space and time and length can change at relativistic speeds. So that's things that we talked about real briefly in the lab. Now, classical relative motion. We've already talked about this, but it's the idea that motion of an object is described relative to another object. Now, on Earth, we talk about it in terms of the Earth. So if I'm walking this way, I say that I'm walking at 2 meters per second. I don't say that I'm walking on the Earth, which is moving very, very quickly, something like 29,800 meters per second. I don't add my 2 meters per second to that, because what I'm doing is I'm assuming that everybody that I'm talking to is on the Earth and therefore moving at the same rate through the solar system as I am. Okay, Earth is the common reference point that we talk about. So because of that, we have velocities can be added, subtracted, and combined using trigonometry. So we said that if I have somebody that's walking towards me, if I want to find the relative velocities, I would add. And the reason why I would add is because if we bumped into each other, it would be a whole lot worse than if we were walking in the same direction. Because my velocity relative to this person is going to be faster. Now, we said if you have people that are moving in opposite directions, the velocity relative to each other needs to be subtracted. The reason for that is I'm going to be moving very, very slowly compared to this person because I'm going to be very, very slowly gaining on them. So if they're moving at 2 meters per second and I'm moving at 3 meters per second, I'm only going to gain at a rate of 1 meter per second. And finally, you can use these things to combine them trigonometrically. Now, in terms of trigonometry, basically what you're doing is you're doing what's called a boat problem. You are accounting for the velocity in each direction. Now remember when we talked about velocity in terms of projectiles, what we said is that each dimension acts independently. And then you can combine these things for an overall velocity. Now, this is pretty much seen in a boat problem as a boat that goes straight across a river with a certain velocity will not end up straight across the river. And the reason why is there is a current that will go this way. Now, these two velocities cannot be added, they cannot be subtracted because they're not in the same dimension. Instead, they have to be combined trigonometrically. So what we do is we draw them just like we did in what's called head-to-tail addition. I have the head of a vector, and I've got the head of a vector, and then what I do is I say, this is my starting point, this is my ending point. Let's see, different color right here. This is my ending point, this is my starting point, and I connect those two things. And when you connect them, what you see is a triangle. Now, whenever you use this, you have a right angle triangle. Well, that's easy to do because you can then use Pythagorean theorem to solve for this. This value right here represents the overall velocity, the relative velocity. So that's how you combine them in any sort of two-dimensional problem. And you see that whenever you have an example. It says people mover is used to help people get between gates on an airport. It says a man is walking 4 meters per second relative to the ground. So the guy's right here, and he's walking at 4 meters per second this way. Now, it says the people mover moves at 2 meters per second in the same direction. So this guy, when he's on still ground, is walking at 4 meters per second. Now he's going to get on a people mover, and the people mover is going to move him an additional 2 meters per second in the same direction. Now, a lot of people will look at this and they'll say, oh, they're in the same direction, so I subtract. And that's not the case. And the reason why it's not is you're not trying to gain on the people mover. You're not trying to see how your velocity is in relation to this. Instead, this right here is going to help you move in the direction. So you've got to think about this. Is this going to make me go faster? Or is it going to make me go slower? And when you think about it, the overall velocity that you're going to get is 6 meters per second. And when you have an overall velocity of 6 meters per second, now you've got a distance. Your distance is 50 meters. Well, this is just a basic velocity equals displacement over time, or 6 equals 50 divided by t. Now when you do this, you would switch those two values and you would get 50 divided by 6, and when you do that you get about 8.33 seconds. Okay. Now the question says, how long will it take to travel? A lot of times you will see questions in here that say, what is the difference between if he holds still on the people mover and if he walks on it? Now if he were to hold still on the people mover, that's 2 meters per second at 50 meters. That would take 25 seconds. So he's saving himself quite a bit of time by actually walking on it as well. Okay, in this next example, it says you have a riverboat captain aims his boat from point A to point B. So he's actually aiming it in this direction right here. Okay, it says the river is 200 meters wide. He does it at 10 meters per second. So this is 10 meters per second, and this is 200 meters wide. Now it says after crossing, the captain ends up at point C, which is 50 meters downstream. So this right here is 50 meters. And I want to know, what is the velocity of the current? Okay, so here's an example of this. It says you have 200 meters that you're crossing at 10 meters per second. So I can do a basic velocity equals displacement over time, and I can get 10 equals 200 divided by t, and t is going to end up being 20 seconds. So in other words, it takes him 20 seconds to cross the river. Now the whole time that he's crossing the river, that he's going this way, the river is going to be acting on him. So for 20 seconds, the current is going to be pushing him to the right. So what I can say is time is equal to 20 seconds. Remember from projectiles that time is the one thing that goes back and forth between the x and y axis. So because of that, you have the whole idea of velocity equals displacement over time. So you could say 50 divided by 20, which in our case would be 2.5 meters per second. That would be the current. So now, the next one says plot a course that would take the captain directly from A to B. Now this is very much an extension question, so you may want to fast forward if this is beyond what you want to know as far as this class is concerned. But if I want to go here, I have to account for the current. So in other words, I've got to do this. I've got to account for the fact that the current is moving at 2.5 meters per second. Okay. I've got to account for the fact that whenever I do this, I can only take this boat and have it move in this particular direction with a certain speed. Okay, now there's two different ways to look at this. The easiest way is to say, okay, he can travel at, I think we said 10 meters per second relative to still water. So that's the direction that he's pointing the boat in. So now it says plot a course. Well, in order to plot a course, really what you're trying to do is solve for this angle right here. In order to solve for that angle, you've got to know a little bit of trig. There's basically 3 trigonometric functions that you're interested in. There's sine, there's cosine, and there's tangent. Now if you were to look here, I have the opposite side of the angle that I'm interested in, and I have the hypotenuse, which I'm interested in. That makes it sine. So sine of the angle is equal to the opposite side, which is 2.5, divided by 10. You can then put this in your calculator. Make sure your calculator is in degree mode, and when you do that, that will tell you the angle that you need to plot your course at. Check your answer with your teacher to see if you can get it correct. Now we come to the idea of special relativity. Now, special relativity is a little bit different. So far we've talked about classical relativity. There are two postulates for special relativity. The first one says that the laws of physics are the same for all inertial reference frames. Basically what that says is the laws of physics as we know them do not change when you go from one place to another. They do not change whenever you go from here to space, from space to Jupiter, from Jupiter to the sun. That the laws of physics are the laws of physics. Okay, the second postulate is the speed of light in a vacuum is c, or 2.99792,458 times 10 to the 8th meters per second. In other words, you have a speed of light that is a defined constant value. Okay, those are the two postulates. Those are the things that we're saying. Special relativity is true if these two things are true. Now, these two things have been proven true, and so we can go on from there. Now, people say, okay, well, what happens if I'm moving at the speed of light and I turn my headlights on? Okay, so for example, I'm in a car, I'm moving at c, I turn my headlights on, light moves at c, therefore the light is traveling at 2c because I add the velocities together, and I've broken special relativity because the light is traveling faster than the speed of light. Okay, here's where it gets tricky. That is not the case. Okay, it seems like it is. It's just like, well, you just add them together and there you go. It is not the case. Basically, what we have been doing by saying that you take those two velocities and you add them is an oversimplification of what really occurs. What actually occurs is this formula right here. You have this, what is called the relative velocity. And what it is it is a combination of the two velocities like we just talked about. But this is the other term. So for example, in classical relativity, what we would say is if I have this guy who's moving in this direction at 10 and a guy who's moving at this direction in 10, we would say that they approached each other with a combined velocity of 20. In other words, 10 minus negative 10, because remember you have direction here and that's important. That's what we would say classically. Now, in terms of when we're talking about things that are faster than this, you have to account for this particular term right here. This is the corrective factor, and it doesn't really matter much until you start to talk about things that are moving closer and closer to the speed of light. Okay, so that's where it actually comes into play. All of the terms in this equation are velocity terms. They're all measured in meters per second. They're all velocities. They're all measured the same way. So let's take a look at this. It says a man runs down the street chasing after his dog. The dog is running at 10 meters per second and the man is running at 12 meters per second. Now they are running in the same direction. So what is their relative velocity using the relativistic speeds formula and compare this to the classical method? So if I was looking at it in terms of the classical method, what I would say is you've got velocity A, you've got velocity B. They're moving in the same direction. So what I would say is 12 minus 10 equals 2 meters per second. And that's what I would say classically. Now if I'm looking at it in terms of relativistic speeds, what I would have to do is I would have to do 12 minus 10 divided by 1 minus 12 times 10 divided by the speed of light squared. So 3 times 10 to the 8th squared. Now, when you take 12 and multiply it by 10, you're going to get 120. But then you're going to take that 120 and you're going to divide it by 9 times 10 to the 16th, because that's what 3 times 10 to the 8th squared is. When you do that, you can expect to get a reasonably small number. And so whenever you enter that into the calculator, you end up getting 1.33 times 10 to the negative 15th, which is a pretty small number. It's basically 0. But to hold true to what we're doing, we would say 1 minus that. Well, when you do 1 minus that, you get a value of 0.9999999999986777777 and so on. So it is a very, 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 very close to 1 number. But just to hold true, if we take this number and we take 12 minus 10 and then we divide it by that number, we would get, let's see, gotta find that button on my calculator, and when we do, we end up getting 2.000000. Let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros. So 14 zeros, I'm not even going to write 14 zeros. And then a 267. So what you can see is that this equation, the equation that we use where we just combine the terms, works very, very, very well for objects that are at slow speeds, that are at classical speeds, that are at speeds that are on Earth. Where it gets tricky, is when you talk about things that move closer to the speed of light. So you have two spaceships that are separated by 0.4 c respectively. The two ships are separated by 1 parsec. Okay, so you need to know what a parsec is, that we'll get to in just a second. But it also says, what is the relative velocity between the two? Okay, actually, parsec's not relevant. What is the relative velocity between the two, and how long does the crew have the rest? So it does become relevant later. So the first thing that we need to do is we need to combine these two velocities. So they're headed towards each other at 0.4 c. So what I can say is I can say 0.4 c minus negative 0.4 c. And that gives me 0.8 c at the top. That would be the classical addition of the velocities. Okay, but now we have to account for the relativistic effects. So 1 minus 0.4 c times 0.4 c divided by c squared. And a lot of times it's easier to leave them in terms of c, and you'll see why in just a second. So now it'd be 0.8 c, and then it'd be 1 minus 0.16 c squared. What I did is I multiplied the 0.4's together and I multiplied the c's together. And when I do that, I get 0.16 c squared divided by c squared. So now c squared cancels out, and I have 0.8 c divided by 1 minus 0.16. Now if you notice, this is no longer 0.9999999 like it was before. This is actually going to have a real effect on the velocity. So when you do 1 minus 0.16, you get 0.84. And now you're talking about 0.8 c divided by 0.84, and that's going to give you a different value. Oh, and we should have caught this before. The formula is actually 1 plus, so this would have been actually 1.16. So let's make sure we go back to our original equation and we fix that it is 1 plus VB V8 over c squared. That makes a big difference. So if you were to look at it in terms of this, you have 0.8 c divided by 1.16, and when you do that, you're going to get a smaller value. And when you get that, you get 0.8 divided by 1.16, and you end up with a value of 0.69 c. So even though the two ships are heading towards each other at 0.4 c, it turns out that they approach each other at 0.69 c whenever you combine them. And people have a hard time dealing with this. They say, well, wait a second, I'm going at 0.4 c, he's going at 0.4 c. How can we approach each other slower than that? And it has to do with the idea of relativity. You cannot exceed the speed of light, even your relative velocities between each other. Okay, now this has been experimentally proven, and we will talk about it, but it gives you this whole idea. Now it says they are separated by 1 parsec. You have 0.69 c as the combined velocities. So the last step for this particular question is we want to know velocity equals displacement over time, and we want to know how long we have to rest. So we have 0.69 c as our velocity, and then we have the displacement is 1 parsec, and 1 parsec is 3.08 times 10 to the 16th. It's a unit, it's an astronomical distance, times 10 to the 16th, and we divided by time. And so now we can solve for the time. Now, whenever you do this, you are going to end up getting a very, very large number, because a parsec is a really, really far unit of distance. So you take 3.08 times 10 to the 16th, and you divide it by 0.69, and then you divide it by 3 times 10 to the 8th. And when you do that, you get about 1.48 times 10 to the, let's see, 3, 6, 7, 8 seconds. So 1.48 times 10 to the 8th seconds. Now that right there is a pretty big number. In fact, it ends up being about 4.7 years. So that's kind of a long time to wait for this particular battle. Just trying to show you that a parsec, a thing that's often referenced in science fiction, is actually a very, very large unit of distance. And even moving at almost half the speed of light, you're still talking about a significant amount of time before you actually meet up with whatever it is. Now, implications of this. Because the speed of light is constant, nothing can exceed c. So, if you have the whole idea of c equals d over t, if this cannot change, that means that these two things can. This gets really tricky. You have the whole idea of time dilation. In other words, time can contract or expand depending on how fast you are moving. Okay, time dilates. In other words, time passes more slowly as an object gets closer and closer to the speed of light. Now, we do have evidence of this actually occurring. And one of the biggest pieces of evidence that you're probably familiar with is the idea of the GPS system. The GPS system triangulates your position using multiple satellites. The more satellites you have, the better it can track your position. But what it does is it's basically making a cross section. It's saying this satellite goes here, this satellite goes here, this satellite goes here, this satellite goes here, and then you have another one that goes here. Now what you're doing is you are located at the intersection of all those positions. However, these satellites are moving relative to you. Okay, so they're going this way, and they're not all moving at the same speed. Okay, they usually go in the same direction, but they're not all going in the same speed. So because of that, in order to triangulate your position with any accuracy at all, there has to be a precise timing mechanism between your receiver on the ground and the satellite above. Now, the satellites are moving faster than you are as they orbit the Earth. So the Earth is moving pretty fast as it orbits the Sun, 29,000 meters per second. But the satellites are actually moving faster. Because they are moving faster, there is a time dilation effect. So they had to do a special relativity time correction. And that special relativity time correction allows us to accurately measure your position usually within about a meter or two. Now, there is other evidence. There are radioactive isotopes. Whenever we slam particles together using a super collider like we have here in CERN, it produces very unstable isotopes. Now, these unstable isotopes are so unstable that whenever the collision occurs right here, they should decay before they get to here. In other words, they have such a small half-life or small lifetime that they will fall apart before they can reach the detector. But we still detect them. And the reason for that is these particles are moving so fast that time is different for them. Time expands, and the time for us standing right here may be 1 second. But the time for this particle may be 1/10 of a second because it's moving very close to the speed of light. And that brings us to the idea of the twin paradox. We have the idea that all motion is relative. Okay, so it is fair to say that, hey, I'm on Earth and I have sent a twin on a spaceship and they're going to some solar system, let's say Alpha Centauri and back, and they move at 0.8 c. Because all motion is relative, it is fair to say that the rocket is moving away from Earth at 0.8 c. It is equally fair to say that the rocket is still and that the Earth moves at 0.8 c the other direction. Well, if time changes, if time dilates, if time expands as you get closer to the speed of light, which twin gets older and which twin will stay relatively young? Because all motion is relative, how do you know which one will get older?